Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to introduce a new way of trying to determine the spontaneity of reactions. And this is one you may actually have heard of before, and that's Gibbs free energy. So one of the big things is right now we know how to predict the spontaneity of a reaction, and that's with the entropy of the universe. However, look at this equation. That's way too many different types of entropy, way too many subscripts. This is a disaster waiting to happen because something will get mixed up. So we're probably going to want to start switching out variables. Well, thankfully, we've already figured out how we can switch out a description of the surroundings with a description of the system by talking about the enthalpy of the system. However, this does end up bringing a temperature dependence, but it will be a lot easier to use. The next big thing is that, honestly, let's be frank, entropy has some really messy units. Joules per mole Kelvin, it's hard to get kind of a good instinct for what that means. So one of the things we can do is try and replace the entropy of the universe, which is kind of vague, with a much better metric that focuses either on a system or a reaction and not just everything. And if we can, it would be really good if we could give it units of energy. So joules per mole or kilojoules per mole or something along those lines. It turns out we can actually do both of these by multiplying the system by temperature. And additionally, to make it more consistent with enthalpy, we'll multiply it by negative temperature. And you'll see why in a sec. So the Gibbs free energy is literally just defined as the negative of the temperature times the entropy of the universe. So using this, we can go ahead and relate the change in Gibbs free energy for any process based on the temperature of the system, the change in entropy of the system, and the change in enthalpy. And you'll notice that now enthalpy and Gibbs free energy are very much in agreement. And now we're just using the entropy of the system kind of to modify the favorability of that exothermic endothermic system. So again, what this is showing is we can think about the favorability of a system being based on how much we order or disorder the surroundings, with modifying that the system may have become more or less disordered itself, which is actually an agreement for how we treated the favorability of a system last semester by simply focusing in on the stability of the system, which is represented by enthalpy. However, it is worth noting that we did make a couple of approximations last time to bring in that description of enthalpy by assuming the system was at constant temperature and pressure, and it turns out those continue. The temperature isn't too much of a concern because it is worth noting that we are assuming a constant temperature as well. We included temperature in our description. However, we will end up figuring out next time how Gibbs will change with that temperature. However, one of the other very important things is that, remember, Gibbs is given as the negative of the entropy of the surroundings, which means this will of the negative of the entropy of the universe, which will have some really big impacts on trying to figure out whether or not a reaction or process is favorable. So using this, keeping this in mind, we can go ahead and look at when a system is going to be spontaneous, non-spontaneous, or reversible. So it is worth noting that multiplying something by negative t won't change whenever something's at equilibrium. 0 is 0, no matter the sign. So just like a reaction is at equilibrium if the entropy of the universe is 0, it will also be at equilibrium if Gibbs free energy is at 0. And we're going to make use of that fairly frequently going forward. Additionally, a reaction is going to be considered favorable. It will proceed in the forward direction if the Gibbs free energy is negative or the entropy of the universe is positive. So again, these are in agreement. However, reaction is considered unfavorable if we have a positive Gibbs free energy. So remember, free energy, just like internal energy or enthalpy, wants to go down. So we go from high, it being unfavorable, to low, as negative as possible, being favorable. So remember, Gibbs free energy, just like limbo, it's how low can you go. However, one of the big things that is also worth noting is, unlike talking about the entropy of the universe, it turns out that the Gibbs free energy has some really useful implications in its actual values. Namely being that if I have a spontaneous process, so remember, there's going to be a negative value, this represents the maximum amount of energy that can be extracted. So if I say we're going to combust methane, if I can calculate the Gibbs free energy of this process, I can figure out exactly how much energy I can use for driving my car. And again, worth noting, this is going to be the maximum, not the actual amount extracted. Similarly, if I have a non-spontaneous process, so I have a reaction that doesn't want to occur, so this would be a positive Gibbs free energy. It means that I have to put energy into the system to make it proceed. So again, very similar to what we talked about with enthalpy. And again, worth noting, where enthalpy was specifically looking at heat, Gibbs free energy can be more or less any kind of energy, electrical, heat, or otherwise. So with this, if I have the non-spontaneous process, essentially this positive value is going to end up representing the amount of energy required to drive a process forward. So negative value, how much energy is produced, and for a positive value, how much energy needs to be put in. Now, worth noting that for a spontaneous process, this is the maximum amount of energy I can get out of the system. For a non-spontaneous, is the minimum amount of energy that needs to be put in. In reality, no process is perfectly efficient. Turns out this does indeed involve entropy. So often we end up getting out a little bit less energy than ideal, and we have to put in a little bit more than we would like. So next time, we're going to focus a little bit more on how we can use these basic ideas and apply them to real chemical or chemical reactions. Until then, take care.